Okay, here we are again. This is part two, the continuation from yesterday. Proving, sorry, this is proving trig identities. Again, the target audience here is yes, you. At this point, we are going to pick up the pace, so the students who have had trig, full course of trig, they're going to be learning new stuff. However, the students from my Algebra 2 class who have not had trig, they are, as long as you did the homework, as long as you followed the previous assignment or previous video, you should be okay. So this is where we left off last time. I just introduced one of the Pythagorean identities. I'm going to restart. So I'm going to create a new slide. Okay, so Pythagorean. So uh, I'm just going to abbreviate Pythagorean identities. Identities. There are three of them, and then after the three, there's like variations of them. So there's three of them. However, there's going to be a little bit more deeper than just three things to memorize or to learn. Okay. So it really starts off with number one, with the one I actually introduced in the previous slide, this thing right here. I'm not gonna I'm not gonna develop it now where it came from. This really has to do with the unit circle, which is like, from previous video, that's a lesson in itself, or more than one lesson, I should say. But anyway, so once you understand, once you kind of like memorize, if you want to call it this is sine squared of theta or x, I'll just use x for instance, plus cosine squared of x equals to 1. So this is a super, super important one. From here, we can generate all kinds of other things literally from here. Uh, on the previous example, on the previous yesterday, I said, well, you could solve for either sine squared or cosine squared. And so this is like what I call, this is what I'm about to say. It's not a new identity. It's based on this. However, this is going to be where it's a byproduct of this. It's going to be useful. As an example, sine squared equals 1 minus cosine squared, which sometimes comes up just the way it is. You're like, okay, I'm good. But also recognize that this could be broken up by factoring into 1 minus cosine, 1 plus cosine, into its conjugates. The conjugate being that it's really the same factor, same thing, except for the plus or minus in between the two terms. It's a binomial. Okay. So that's going to be an important thing in itself. Let me see if there was anything else to be said specifically about this. Of course, what if I have, let's say you come across uh, a question like this where you recognize something where it's cosine squared minus 1, and you're like, well, that kind of looks familiar to this, but notice how my signs are reversed. The cosine should have a minus in front of it, and 1 is a positive 1. So that just means that this must be a negative sine squared. In other words, if I were to multiply everything by -1, I'm going to get back to the original, right? Like this is the original. This is super important because this is a byproduct of the big one. This is the most important identity. We kind of, well, when I say the most important meaning out of Pythagorean identities. And from this, I could generate all kinds of new identities, including like a byproduct. So as an example, right, and this is just using at this point, this is using the pure algebra skills. It's not even involving trig. If I have cosine of x minus 1 somehow times cosine x plus 1, well, I recognize that that's just the negative version of this. I mean, hopefully you see that. Not in here, there's nothing, it's really the same thing. But this means this is a negative version of that. This must mean this is negative sine squared, okay, which is cosine squared minus 1. So all of that, this really becomes your success on this depends on your success or your knowledge and comfort with just basic algebra, like manipulating algebraic expressions. Okay. Again, remember, like for my Algebra 2 classes, treat these things like sine squared. It's just an object that you're just changing the appearance, you're manipulating, you're adding to another sine squared as an example. Okay, anyway, enough about this. So let's develop. So this is number one, right? This is the first one. Right from here, we're going to develop two more. And each one of them will have its own byproduct things. Like this is what I call byproduct of this. Okay, so what if I were to, since this is an equation and this is a fact, right? Like this is a fact. This is just accept it. Bless you. This is a fact. So if I divide both sides by a number, I'm allowed to do that, right? Like just I'm not proving anything right now. I'm just kind of developing a new one. So what if I divide everything on the left side and the right side by some number? As an example, if I divide everything by 5. Well, I'm allowed to do that. Now, clearly, dividing by 5 is kind of silly. It doesn't really, change anything. But the point is, what I am allowed to do. This is an equation. I'm allowed to use algebraic properties by dividing things by something. Well, I'm going to choose to divide both sides by, let's say, by cosine squared. I could have started off divide by sine squared, but you'll see why it's kind of a little more convenient to divide by cosine squared. Eventually, I will develop by. So the second part, if I divide this, oops, something just fell. My microphone just fell. Let me set it back up. Hopefully that did not interfere too much with the video. All right, if I divide both sides, in fact, I'm going to rewrite it. So this is going to be like this is sine squared plus cosine squared equals to 1. And it's an equation, and I'm going to come across and I'm going to divide both sides by cosine squared. But I'm going to do it individually so that it's easier to see what I'm doing. So I'm dividing everything on the left side, everything on the right side by cosine squared. Cosine squared, cosine squared. And again, I'm being neglectful with not writing letter x for simplicity and for just efficiency. Well, what's going to happen here? Well, this, by your previous knowledge, this is just the tangent squared, right? Sine divided by cosine, but you can think of sine kind of like this, squared divided by cosine, and each one gets squared, right? That's what this is. So it's tangent squared. Now, what is cosine squared divided by cosine squared? Well, that's automatically 1, because anything divided by itself is 1. And what is this right here? Recognize that that's really 1 divided by cosine, kind of like this, squared. That's at what? Secant squared. Okay. So we just developed a brand new identity. Yes, this is an identity. This works every single time, no matter what the value of x. If you plug in x in here, or I use a different color, x in here, or theta, this is going to work. However, right from here, we could develop brand new things, right? Like I cannot factor this. So if I come across something in the problem which says tangent squared equals, tangent squared plus 1, well, I know that that's secant squared. I could rewrite it as that. But what if I come across the tangent squared by itself? And I want to convert that to, well, that's just secant squared minus 1. I just use algebra, manipulate that. Okay, but that also gives me another ability, or another way to rewrite that. If I factor this is like a squared minus b squared, right? Like where b is 1, it's 1 squared. So using that very, very useful factoring technique, I could factor this into its own conjugates. This is secant minus 1, secant plus 1. That in itself is important because might come across where I come across a problem where I have this and I could do something with that. Meanwhile, without this property, I have no idea what secant of theta plus 1 is. I just don't know. It depends on one. I'll stop right there. Okay. So this comes up with a new technique, or develops a new byproduct of an identity. But also, what if I were to do this? What is the how else? How can I if I isolate one, meaning one equals secant squared minus tangent squared. So what did I do here? Well, I simply subtracted tan squared from both sides. I isolated one. Remember, one could also be written, many, many ways, including sine squared plus cosine squared. So knowing all of these things will give me more liberty, more freedom to kind of manipulate things as they come. If I'm dealing with sines and cosines, this is probably what I want to convert to. If I have a whole bunch of tangents and secant squareds, I might want to think of it this way. Anyway, how else could I factor this a little further? Well, again, for the difference of squares, this is secant minus tangent multiplied by secant plus tan. Right? Look at that. That's so it depends on a particular situation. And the more problems you do this, the more not only you become more comfortable with it, but it becomes really, really enjoyable where you're like looking at a very difficult problem. You're like, oh, this is, you're stuck, but yet all of these skills come kind of hopefully come rush into your forefront of your thought. You're like, wait, I could do this, or I could do that. Um, Now, on the other hand, what if I had this reversed? What if I come across a problem and it says tangent squared minus secant squared? Well, that just means that if I multiply, so somebody came across this, that's an identity. We developed it from this. And they just kind of flipped the signs, the pluses became minus, minus became plus. That means this must be -1. Look at that. All of a sudden you have just from the now I don't want to say basic because it's really yes, it is basic, but it's super, super important from this. Look how many different identities, how many different equations we could come up with, and we're not even done yet. So in this case, it's I have tangent. You could factor further, which would just be reverse of this. Okay, so this would like tan minus secant, and this is tangent plus secant. And I do this as I need it, like for a particular problem, okay, which I'm trying to fit into a given problem. All right, let's develop number three. Number three. So meaning there are three major identities, Pythagorean identities. So number three is, well, again, we're going to start with or mother of all identities. Sometimes as a joke, I call it because from this we can develop. So this is what? Sine squared plus cosine squared equals to 1. That's the one that you must know. Like if somebody wakes you up in the middle of the night and says, "What? Quick, give me this identity." I'm like, all groggy, but you come up with this. Anyway, now what if I divide everything by, instead of cosine, divide everything by sine squared? And again, I'm allowed to do that within its domain. Yes, I understand that sometimes sine of x could equal to 0. There, technically, I'm not allowed to divide by 0, but that's, we kind of get away from that limitation by saying, well, within its domain, I'm allowed to do this, whenever this is not equal to 0. Okay, good enough. So what happens here? Um, that clearly that's 1 plus, well, what is this? Cosine divided by sine, and each one is like sort of squared. You could think of it that way. So cosine divided by sine is cotangent, and it's squared, equals, and this is cosecant squared. So, cotangent goes with cosecant kind of thing. Uh, in the previous example, tangent went with secant. It's just a matter of like where that one goes, whether it's a +1 or a -1. Like when I say -1, yeah, in here it's gonna be plus. But if I wanted to solve for one of these variables, as in a cotangent squared equals, well, that's just cosecant squared -1. And again, I can develop other byproducts of this by factoring, by manipulating things. Um, so here, from this, I'm going to develop like sort of three other ones. This is one, and what's inside here is cosecant minus 1, cosecant plus 1. Then if I'm going to solve for, I'm going to solve for 1. Literally, 1 equals cosecant squared minus cotangent squared. And if I need to break this further, well, I can. This is a difference of squares. So cosecant minus cotangent, cosecant plus cotangent. Okay, look at that. So it really depends on what your needs are for a particular problem. Okay, I said I'm going to develop 3. Let me see if I can develop 3. So if I solve, I already solved for this. I solve for this. I mean, this is already. Now, by the way, can I factor this? No, because of the plus. I cannot factor that. Uh, if if on the other hand, if this was a minus, like here, like what if I have 1 minus cotangent squared? Can I just write, oh, negative cosecant? No, no, because all I did was I changed one of the side, I didn't change this sign. So, but what can I do here if I really wanted to do, well, I could factor it maybe, because now it's a difference of squares. 1 minus cotangent, 1 plus cotangent. If I need, this. It does not equal to negative cosecant. I just want to emphasize negative cosecant. And it really depends on your, algebra. I don't want to say algebra 1 because this, even though, yes, this is algebra 1, just manipulating, pluses and minuses, but obviously we don't do anything close to this in algebra 1. All right, so this would be incorrect. Like this is wrong because there is a, it's just impossible for me to get from this with, to this by changing only one sign. On the other hand, if I, change both of them, yeah, that would be just the negative of that. Okay. Let me see if there's anything else. So I would recommend, especially in the beginning, although I don't do that. Like I'm here, I'm telling you, do as not what I do, but like it still is a good idea. Um, so kind of memorize this. I'm just really bad at memorizing things, like because I could develop this. So let's actually try to remember this. So tangent squared plus 1 equals secant. So tan squared plus 1 equals secant squared. Okay, and what's the other one? And frankly, I don't memorize it. I just basically like come up with this on the spot. This is the one that everybody should know off the top of their head, right? Equals to 1. And from here, I can generate the other two just instantly, but just kind of in my mind recalling, well, if I divide everything by sine square, I'm going to get this as 1 plus cotangent equals, if I divide this by sine, this is cosecant. Oh, cosecant. Sorry, it's kind of messy right here. Let me just clean that up. This is cosecant squared. There, I just without memorizing it, because I'm just have a mental block on these things. Uh, Hopefully, if it's easier for you to memorize it, do it. Just kind of do it like this. Have it on a 3x5 card for a while until you are 100% comfortable. I don't do that. If this, I still remember from high school days, the first thing I would get it on a test, if I get a test and I write this down, and on the side here, I'm going to write these very, very quickly just by generating them mentally. So let's do it again. Let's just demonstrate. So this is the number 1. Everybody knows this one. So the second one is I'm going to do mentally, I'm going to divide everything by sine. So this is 1 plus cotangent squared equals 1 divided by sine is cosecant squared. Now I'm going to do the same thing but divide by cosine squared. So this becomes tangent squared plus 1 equals secant squared. So there, it does slow me down in the sense that I have to do this mentally, and it slows me down by literally like 5 seconds. And frankly, even when in my calc classes, I tell my kids this is how I do it. I don't expect for you to memorize this because once in a while in calc it also comes up. In calc 2 it comes up a lot more. In calc 1, in AB, yeah, I'm sure it comes up, but not as often as calc 2. Anyway, so those are the Pythagorean identities. IDs. Okay. And from here, we it opens up a whole new a realm of possibilities of solving, identities. Well, let's do a couple of examples and practice. Okay, so okay, this title should have been way up front. We just did this. We just developed all that. Okay. All right, so here's an example. I think very simple. So this is not even identity because they're not telling you what it's equal to. But I'm just gonna say, excuse me, I'm just gonna say, well, let's make it into identity. Let's see if the other side is just give me either one or let's say it's sine. I don't know. Sine squared. Okay. Or it literally is could be like let's could be one. Maybe everything cancels away and it's and I frankly I didn't even look here yet to see what but let's see. Well, actually this one is so simple that I recognize immediately that the answer is going to be this. Okay, so here we go. So the way to see that is um, now you could rewrite as an example, you could rewrite what sine squared is because when they multiply, they don't simplify. They do not. Sine times cosine does not simplify. It just stays that way. Now, there are more advanced, like this could be, let me see, what could this be? This is sine of double angle divided by 2, but that's irrelevant at this point. Sorry, I shouldn't have done that. So in other words, they do interact, but at different levels. Okay. But right now they don't interact. Well, I could rewrite this, the sine squared. I could say, well, this is just 1 minus cosine, kind of like this, and open the parentheses and maybe do something. I don't know. But hopefully it's much clearer. Like in this case, I see something in the denominator that really jumps at me. This is cosine squared. So, but if this is cosine squared, look what happens. Cosine squared and the cosine squared goes away. So you could say all of this goes away with this part, leaving you with just this. And there's nothing you can simplify. You can't simplify, sine squared by itself. Now the sine squared equals sine squared. So yes, this would be an identity, not one, right? Like that would not be an identity. You could also say, well, the other side could have been 1 minus cosine squared. And that would also work because remember, sine squared equals that. Okay. Again, we could just at this point, well, it's almost like not showing off, but it's just kind of like, well, what else could we do here? What else? Yeah, 1 minus cosine. Basically, factor into its conjugates, 1 plus cosine. You know, and this you can't do anything with. You cannot simplify without the squares. Um, okay. Just an interesting thought. What can you simplify this? 1 plus rewrite this as something, right? Like as something. You're like, oh, it is tempting to say, oh, maybe it's something to do with sine squared, or maybe neg because like, oh, anticipate. No, you really can't. This, in order for this to be the case, this must be minus. Or they're both kind of like change them both, but you can't just change one side, one sign on one of the sides, and that's it. So this is false. this is false, right? So in fact, false. But what can I do here? Well, if I'm like forced to do something, it's like I gotta do something, and very often that is the case. You're like, I'm stuck. I don't know if to do something. Uh, I could do this. I could say, well, one is really a fancy way of writing sine squared plus cosine squared. That's just one. And then I have plus cosine squared. So this could simplify to be, and if you want to call it simplified, sine squared plus 2 cosine squared. And this is why that one really does not simplify, because this doesn't simplify. There's nothing I can do here, right? Like there's just this extra cosine in there. If this 2 wasn't here, that's just 1, but that's what this is. Anyway, so the point is sometimes you're stuck. Um, and you have to try something else. All right, let's go on next slide. All right, so two problems here. Let me see. Yeah, two. So this was easy. This was two problems, and in this case, verify an identity. Okay, let's take a look at this. And at this point, I am going to be demonstrating techniques. Now, it may not be, you know, well, I was going to say obvious, but nothing's really obvious immediately. Uh, like here, the obvious thing is like, oh, let's convert this maybe to sine. Sorry, yeah, convert the sine squared into 1 minus cosine squared. Okay, that's fine. How does that help you over here? How do you kind of see a connection? Not obvious, not obvious at all, but okay, I see. So that was like sort of like a dead end. You try and it doesn't lead you to an the next you don't see the next step. So I'm gonna introduce a technique right there. Looking at this now, you could remember from the slide one or video one, convert everything to sines and cosines, right? You could, and you say this is cosine like this minus cosine divided by 1 minus cosine. And that becomes, well, in this case, it's really not the way to go. I see a much better way of doing it. Okay. Okay. So this would not be a good technique. This would be like another, not really a dead end, but it would lead you to like, oh, you got to combine them together. And, like, well, actually, oh, that's not bad. Cosines do, if you put, yeah, you could use that. I mean, I just did this mentally, what, three steps ahead. It will get me to this. But there's a better way of doing it. This is a fraction where my numerator I'm allowed to split, meaning this is this fraction minus this fraction. Denominators, you're not allowed to do this with. You're not allowed to split your denominator. But numerators, yeah, you can split because it really was, this is like I started off, secant, sorry, let me clear this out. So this is secant minus cosine secant. That's what I mean by split. So from your pre-algebra, whatever, days, if you have a common denominator, you're allowed to combine your numerators, right? Like, but in this case, I'm actually going the opposite direction. I'm simplifying because I want to, well, this part is just one, right? Like everybody's, seeing that's just one. And what is this part? Well, cosine divided by secant, that secant comes, when you would divide, this right here is the same thing as cosine, and this is 1 divided by cosine, right? That's what secant is. And that cosine comes up because when you divide it by a fraction, you multiply it by its reciprocal and so forth. This really becomes cosine squared, this part. And if that's the case, well, this instant recognition after, like a little bit of, it's from Pythagorean identities. Well, this is just sine squared of x or theta, whatever. Yeah, theta. And that's exactly what's on the side. So in this case, I wanted to manipulate this side by using algebra skills, just algebra, and then a little bit of trig, treating cosine divided by secant as these things. Like I don't even know what they are. Like for my algebra 2 class, you don't know what they are, but just treat them as things as, like when you divide by a fraction, you multiply by the reciprocal. So this cosine comes up, becomes cosine squared. Okay. All right. So that. At any time, if I'm going a little too fast, this is the video after all, you can pause, think of it yourself before you say, this is hard. This is not. These problems are, they're puzzles. Some people find puzzles difficult, but some people, thrive on that. All right, next one. So we got this. Next one here, over here. Uh, so this, I love seeing, sines, squares, or cotangent squares because we could do stuff with that, right? In this case, I could convert everything to sines and cosines, right? Like I already have the sine squared, so I could convert this to sines. But I recognize, wait a second, right here, 1 plus cotangent. That's nice. That's a what? If you have instant recall, oh, okay, I got yeah, it's this, right? It's what was the thing here? Yeah, right there. 1 plus cotangent squared is what? 1 plus it's this. Okay. If you didn't recognize that, you could still develop it on your own. You're like, wait a second, I recognize, like there's a relationship between these two. Let me do it from sine squared plus cosine squared equals to 1. And let me get into how do I generate a cotangent out of this relationship if I'm going to divide by sine squared. So this is how I would do this without looking back to the previous slide. In my mind, I would do this. Again, I for some reason, I don't know why, I have I have a difficult time memorizing this. But by doing this, this is 1 plus cotangent squared equals to, well, what is this right here? Well, I'm going to leave it as 1 over sine squared because I'm going to be using it here. So this really is 1 over sine squared. But what's in front of it? Sine squared. And of course, they do what? Cancel, leaving you with 1, and yes, we just verified that. So that was a pretty easy application of one of the Pythagorean uh, identities. Now, I am sure there's more than one way. I'm sure if I open up the parentheses on the, maybe kind of call this into 1 minus cosine. I can also, and then multiply it out and so forth, and stuff will count. I know it's going to get me there. May not be, very efficient, but the point of what I just actually am making is there's always more than one way of doing it. Always. That's one of the things. I mean, it's also like, because it's a puzzle, there's typically more than one way of solving a puzzle. Okay. All right, let me clear this out. So again, look back, pause it, kind of look at it, stare at it, said, oh, this is recognizable. I know what that is. It's 1. It's cosecant squared, right? But remember, sine times cosecant equals to 1. So if you square both of them, it still is that. It still is 1. Okay, so yeah, there's, okay. All right, let's clear this out. Go to the next one. So can they get more complicated? Oh, of course, of course. Let me see if this is how, yeah, I mean, I have a couple of, problems here that are, um, well, it's in some, I forget what this means. I think this is extra difficult, like a challenge problem. And notice the fact that this is out of some textbook, the fact that this is like number 49. Usually in the textbook, in the back of a chapter, they start off the first 20 are easy, then intermediate, and like more challenging problems. And so this is intermediate to a challenging. It's number 50, 49. It's pretty high up there. Okay, let's do it. Okay, we did this. Okay. Now remember, one of the strategies, you only work on one side at a time. You can't just like, hey, I'm going to multiply both sides by sine as an example. You can't do that. Um, but you pick a side and you work on that side, and you typically pick a more challenging side. But in this case, they're kind of the same difficulty. They're, like they look more or less the same. Now, I mean, I could see the way. In fact, I'm going to do this. This is a really good problem to demonstrate. You can do it more than one ways, more than one way. Really, really good problem. So, but what jumps out at me right now is I think I'm going to start on the left side because I immediately see I can separate this into two fractions. Whereas I am not allowed to do it this way. In other words, this side you're not allowed to say, well, it's really sine over 1 minus sine over cosine. You cannot break up your denominator, but you can break up your numerator. Okay, so I'm going to start with on this side. Well, and this is what right here. This is cosecant. Hmm. Is that gonna yeah, okay, I cosecant, so well let's see. Let's see. So in fact, I think that might be not a dead end necessarily, but it would take me a look at, in a longer path. Remember, this is like a maze. You might just require more. So, but one of the things, this is cosecant plus cotangent. Okay. Well, I don't know a relate if without the squares, I really don't know the relationship between them. There's really no direct relationship. Um, and so it feels like I'm stuck. Okay, I am kind of stuck. Um, yeah, yeah, I see that. That's beautiful. Okay, that's beautiful. I am stuck right now. So for me to get out of this, I almost have to like go backwards to this which so in other words I hit a dead end and I backed up away from that wall to what I started with and I could do something else and I'll demonstrate that in a minute. I'll demonstrate that which is not obvious at all, but that's when you acquire different algebraic techniques. Okay, so I'm going to start actually on this side, which feels like, well, I really can't split this up. That's fine, I'm not allowed to split that up, but I'm gonna demonstrate a really important technique. Okay, so what I am allowed to do to this is multiply it by 1. Right, I'm allowed to do that. Like anything times 1 but I'm gonna make it a fancy one. So as an example, could I do this? Sure, I'm allowed that because this is a 1, but obviously that would be like a silly thing for me to do. Like, what's the difference? 5 and 5. Yeah, yeah, I'm demonstrating that as long as and I'm seeing what to multiply by, as long as I multiply top and bottom by the same number, and I'm only dealing with one side at a time. I'm not doing it to both sides. I'm allowed to do this. As long as I do it top and bottom by the same number or the same expression, I'm good. But here's where the skill comes in. I'm going to multiply by the conjugate of this. Now, so, well, where did that come from? Yeah, knowing this is such an important property that it comes up all the time. So what this is going to be is like, what's my conjugate here? Well, it's the same thing, just with a different sign here, plus cosine. So that's going to be and that means I multiply the top by the same thing. Make sure you understand, like, oh, I don't multiply this by plus, but this is a minus. No, that would not be a 1. Okay. Now the beauty of this, or seeing this, we're like, well, that's just multiplying two conjugates. That tells me that using this property, if you were, imagine foiling that, which I absolutely in this case hate to even call it that because you just recognize that the denominator should be 1 minus cosine squared. That's what the denominator is. Yeah, the numerator is still what it is, right? Sine, and I did not open the parentheses because I see where it's going, plus cosine. I'm going to leave it like this, like do not distribute, because you're only going to complicate things. The goal here is to manipulate and cancel, reduce. Well, what is this right here? Isn't that just sine squared? It is. And look what I like I have a sine squared here, but I have a sine in the numerator. I'm going to, in the next step, I'm going to rewrite that, but basically I'm canceling this versus this. Do you see that? Okay, pause and think, so after I cancel, I'm going to have 1 plus cosine and divided by what? Well, what there was sine squared. The square I canceled away, and this is sine. And look at that. Look at I'm there. Isn't that exactly what the other side is? So that was the skill. The skill there was, and in this case, it didn't feel like I'm using Pythagorean uh, identities. Well, technically, I was because what I was doing is I was well right there. That's a Pythagorean identity. I made this into a sine squared. It's a byproduct of sine squared plus cosine squared equals to 1. I just recognized that, wait a second, if I have 1 minus cosine squared, that means you must have been this, sine squared on this side. And that's what I used here. Okay. And yeah, this is a really good technique. Multiplying whenever I see, I love seeing, first of all, I love seeing sine squares and cosine squares or tangent squares and so forth. But if I don't see that and I see a combination of one minus one of these with a single power, my mind almost immediately goes, what if I multiply this by its conjugate? Let's see what like that is that gonna get me that. All right, in fact, I'm gonna stay on this problem. Just gonna give myself a little bit more space. I'm gonna erase all this, uh, delete that, and I'm going to move this over here, right? And I'm gonna show you a different technique, a different not technique. It's the same. It will be the same technique, but the point is, it'll be I could start on in this case. I could have started on this side because I see where it's not that where I went wrong. It's just that I used the wrong technique, and I recognized it because if I were to split this up, which often is a really really good technique, but in this case, it led me to kind of like a dead end. Like I didn't know what to do with it. When I separated them, but if I were to do this and say, well, wait a second, if I'm allowed to, rationalize or what's sometimes called multiply top and bottom by the conjugate, I'm going to do the same thing over here. I'm going to multiply top and bottom by the conjugate of the numerator. So that means I'm going to be multiplied by 1 minus cosine, and this is going to be 1 minus cosine. I'm going to multiply top and bottom by that. What's going to be up top? Well, up top is going to be 1 minus cosine squared, right? If you were to FOIL but yeah, you should just recognize that. And what's going to be the denominator as well, I don't want to distribute because I have a feeling and I'm pretty confident that it's going to cancel. So I don't want to distribute this into, I definitely don't want to do this because there's nothing I could do here, right? Like, so I'm going to leave it as sine. Oh, this sine, or actually, I'm going to do a little bit of a clue. So this is, oh, God, 1 minus cosine. This is what this is times sine. Okay. I just, the goal was there to manipulate the numerator to become this. Because here I recognize this is what? This is sine squared. And now well, wait a second. I have sine squared up top. I just canceled against sine squared, the square part with a sine, leaving you sine divided by 1 minus cosine. And that's exactly what's on the other side. So that's a proof. We are done. Okay. Yeah, yeah. So in this case, it didn't matter which one I started with. The goal there was to, well, not the goal. I mean, it's a technique was to recognize, hey, it's a multiplication by the conjugate, either numerator or denominator. Okay. All right, let's continue, or let's clear this out. Uh, and I think this might be the last one because I think this video, I can't really tell how long this video is, but I have a feeling it's getting long. All right. In fact, more of the same. Looks like it's the same. Um, by the way, right, like by the way, this is why you're not allowed. Like if I came across this, you might be tempted from your algebra one or a pre-algebra. Hey, what if I cross multiply? And that is absolutely key. I mean, yeah, if you were to cross multiply this to the top and this to the, look what would happen here. 1 plus cosine x times 1 minus cosine x, and the other side is your sine times sine is sine times sine, sine squared. But you recognize that this is, well, this is 1 minus cosine squared, which is sine squared equals to sine squared. Yeah, it feels like, yeah, this is proof. But remember, in proven identities, you're not allowed to touch two sides at the same time. You're not allowed to cross multiply. It's just think of it as just. I mean, there was actually a very good theoretical reason why you're not allowed to do that to prove that one side equals the other side. Although if this was solve an equation, yeah, that's exactly what I would do. I would just cross multiply and yeah, this is true. Anyway, so in this case, yeah, I can't do that. So I think maybe I should leave this up to you for like individual practice, but I think almost clearly this is going to be what you multiply either one by its conjugate, right? Like you multiply the conjugate here would be 1 plus cosine, 1 plus cosine. Wait, is this the same thing? Oh, we just did. Wait, that was crazy. I'm like, no, what? I'm redoing the same thing. Yeah, sorry about that. They after a while they looked very similar, and I'm on like I could be doing the same problem tomorrow and not recognizing it's the same because they it's all about skill, not necessarily about memorizing what the answer was. In this case, the only reason I recognized it is I literally did this like what 30 seconds ago. All right, so let me do this one. Oh, okay, yeah, this is a good one. Yeah, this looks pretty hard, and the fact that it's like in this color, I felt like maybe this is what they call a challenge. Okay, so what's going on here? Well, I have some fraction and have another fraction here. You might be tempted to and I don't want to say you can't do it. In fact, I'm pretty sure you can do it. Separate this into, two separate fractions. Okay. But the problem is you can't separate this is not allowed. You can't do it here. This is you're not allowed to do that. Okay. Um, but I almost want to say I guarantee you could still do this and do something with this and manipulate and use your algebra, your fantastic algebra skills. Okay. All right. Um, all right. You could pause it, observe. So clearly I'm going to start on this side. Not that I'm going to make this. Okay. And well, let's see. I don't see instantaneous. I'm seeing 2 steps ahead, but I think I might need 3 or 4 steps ahead. I'm gonna multiply top and bottom. I'm gonna multiply this by its conjugate. I wonder if I should do the same thing over here right away. Maybe. Yeah, maybe. Oh, yeah, yeah, yeah. We can do it. I can do it 2 different ways. Yeah. I like this problem. Okay, let's multiply by the conjugates. So what do I have here? I have 1 plus sine 1 minus sine, right? Let's see where that goes. And down here I have, well, I have a cosine to begin with, right? Like this cosine. That's basically, this part is what I started with. But then I have to multiply top and bottom by 1 minus sine. Very similar to what we just did a couple of minutes ago. Okay. So up top it's going to be what? Up top it's going to be, and I might as well do it, continue with this part. So I'm going to go a little quicker. Over here, this is going to be cosine, and the conjugate of this is 1 minus sine. Leave it like that. And this is going to be 1 plus sine, 1 minus, 1, 1 minus sine. Okay. Rewriting this, the denominator is fine where it is. Let's see. And this is, the numerator here will be 1 minus sine squared, which is cosine squared. So I have cosine squared. Okay, yeah. We're almost there. We're almost there, I think. So cosine squared. Down here I have a cosine and 1 minus sine. Okay. And over here I have plus, and similarly you have cosine 1 minus sine. And down here this is the same thing. This could be cosine squared. Cosine squared, right? Okay. Um, how's it going to simplify? So this is cancels with this, and similarly this cancels with this, leaving you with cosine divided by this, and this divided by that. So it feels like I really didn't help myself. I'm sort of in the same situation. Now, yeah. So it's not necessarily a dead end, because I could probably take it from here as well, but I am going to back away and say, well, maybe a different technique, because I could see that this becomes sort of repetitive. If I multiply top and bottom by the conjugates. Give me a second. Um, oh my gosh, I think I overdid it. I think I overdid it. I love this. This is great. So okay, so because I recognize something from here, I recognize I can do this a technique from here. It's like, wait a second, I could have done it over here as well. So this is a real, yeah, no wonder this is in this call. This is definitely a higher end thinking problem. So it's not that what I did was wrong. It's just that it's not going to get me to the answer as quick as it could have. I'm going to do this. In fact, I'm going to treat this side. I think this is good. Everything I did here was okay, because I'm not allowed to split my denominator, right? Over here, my numerator, I really could have split. And I'm going to see where this goes. What is this versus this? Well, this is what? If I 1 divided by cosine, that's secant. Okay, we're good so far? And what is sine divided by cosine? Well, that's tangent. Okay, that feels like, well, it didn't really do anything, because now you just made it more complicated. Instead of dealing with only sines and cosines, you're dealing with this. And I kind of peek and I see, well, the other side is secant, so I don't mind seeing a secant on this side. In fact, there's 2 of them here, 2 times. I'm hoping to cancel the tangent, and I think I see where it's going to cancel. So everything I did over here for rationalizing, well, not rationalize it, using the technique of conjugates in the denominator, I'm still okay with. I want this. But watch, yeah, this is beautiful. So this side, I did everything I could have, and I'm just going to leave it this way for a second. Plus tangent, right? Yeah, this one is the one that I require a little bit of manipulation. So I multiply top and bottom by the conjugate. I simplify it, but now my denominator is nice and simple, and I'm gonna split my fraction. I could not do it before because the fraction was the denominator was a two-part denominator. Now my denominator is one part. And so what is this right here versus what is this right here? See what I'm saying? I'm going to split them up. And so what I have here, and this is, I already see the answer. This is secant plus tan plus, well, what's this part? Well, that is secant again. And what is minus or negative minus sine divided by cos? Well, that's tangent. And look what happens. That was great. Look what happens. Tangents cancel away, leaving you with what? Secant plus secant. Well, they don't cancel, they combine. 2 secant theta or whatever. And the other side was, the other side was that the whole time. So this drops down all the way to the end, kind of like this, all the way to the end. And this is 2 secant squared. No, by force of habit, I wrote squared. Secant theta. And we are done. That was great. Uh, so the skill there was a combination of things, and it was seen 3 or 4 steps ahead. The first time I did it, I kind of saw only 2 steps ahead, and I hit a dead end. But I was like, wait a second, because then it becomes repetitive. That means I should have done something at the beginning slightly different. All right. Let me make this a little bit smaller so I could fit all in one page for you to kind of grasp and admire. Because I like that problem. Let me see, group that Alt G and group it, kind of make it a little smaller and full screen. Okay, yeah. Yeah, I like that problem. So go ahead and if you want to pause it, study that what I did. Initially I hit a dead end, but then I split up this fraction into 2 parts. But on this part, I multiplied by top and bottom by the conjugate of the denominator because sooner or later, like in order to get rid of one of the cosines, I do want to bring in cosine squareds. Like whenever I see something like this, my mind goes to like, I could create something square. I could use Pythagorean identities, even though it's not obvious that you can. Okay, that was a great problem. I want to say I guarantee that I could actually do it another technique. Let me see if I can, like, can honor that guarantee. Yes, I could see another technique, and I don't know which one I prefer, but the fact that you can do more than one, I mean, that this is what like I find so exciting about this. All right, this is I'm gonna create a common denominator. Basically, I have 2 fractions here, and what happens when you have fractions that don't have anything to do with it? The denominators are not common. As an example, 5/7 plus 3/9. Boy, no, that was stupid. So 3/10. Yeah, 3/9 is just 1/3, which I could have used. Yeah. Well, what do you do with it? You multiply your denominator, right? So to create a common denominator between both of them, that would be that. And then you do whatever, this is algebra or pre-algebra skills. But now we're gonna do pre-algebra, this skill on steroids. Like this is gonna be, well, I'm gonna multiply, my denominator is going to be cosine of theta, I'm actually being formal here, writing theta, times that 1 plus sine. And we'll see where that goes. But I'm pretty sure I see where it's going. Okay, maybe not. We'll see. Okay. So what's going to happen over here? Well, this is going to be 1 plus sine squared, right? Because I'll multiply this. And this is plus cosine squared. And hopefully you're seeing where I got that from. Okay. All right, let's keep going with that. Well, this distributes, like in order for me to combine that, because I know I'm gonna have sine squared here and cosine squared. I like that. But in order for me to kind of get to it, I have to distribute this. And remember, this is like a plus b to the second power. You don't just say a squared plus b squared. This is like one of the mistakes that drives me crazy when kids do this. This is not true. There's a middle term, right? This is false. There's a middle term, a squared plus 2ab plus b squared. So over here, I can do this pretty quickly. This is going to be 1 plus 2 times sine plus sine squared. Okay. And remember, I still have a what? Plus cosine squared from here. Now here, I don't want to distribute. I absolutely don't want to distribute because I have a feeling I'm looking to cancel stuff. So I'm going to leave it factored form, cosine 1 plus, that's a 1 plus sine. Okay, that's just that. Okay, let's keep rolling. So what happens here? Well, this is nice. This part right here is what? That's just 1. Sine squared plus cosine squared equals 1 immediately. So I'm going to combine this 1 with this 1 over here. And then I see there's a common factor 2 between them. I love that. Look at that. Look how difficult that looks, and yet there's just something elegant about it. Okay, so I'm gonna take the steps, one step at a time, even though I in my mind I already solved that. So 1 goes over here. This becomes 2, and so 2, and the common factor is 1 plus sine sine, right? Like there it is, right? We just factor. Remember, like this became 2 here, and now a common factor 2 comes out, leaving you 1 plus. Now what's in my denominator the whole time? Well, denominator I don't touch. Cosine 1 plus sine. Look at that. Hopefully you're seeing, and hopefully you are, as joyful as I am right now. Look at that. That goes away. And what is 2 divided by cosine? Well, anything divided by cosines, you could rewrite that as 2 secant of theta. And what's the other side? I mean, we're went as far as we can go. And the other side is that. So 2 secant theta, and we just proved it. And I think we might stop here because there's no end to this joy, but but there's an end to the video. Okay. Um, let's see if there's a look. I want you to kind of absorb that because this felt really difficult. Like that first step felt more difficult than the other, but in fact, I think it was easier. Uh, yeah, all I did was I added 2 fractions together, and they are complicated fractions, right? They're not your algebra 1 or pre-algebra fractions, but they are trigonometric fractions. So again, let me make this kind of smaller so that I could fit all of that uh, and control and make it a little bit smaller. Yeah, I actually like this particular method a little bit better. Okay. All right. Is that the last problem? I think it is. Yeah, yeah. I didn't want to go too far into very exotic solutions. I mean, this was a good one. Anyway, I think we'll stop, and maybe I will make a video number 3 to kind of pull some really difficult looking problems. I mean, this is, after all, for my Algebra 2 class, this is an enrichment. However, for, like a good, for a pre-calc honors class, and, hopefully I'll get to teach that, or even for AP for that matter, AP pre-calc, now that thing, there's such a thing. This is a really good, just ability to manipulate trig identities and trig expressions. All right, I think I'll stop. This is probably more than a half hour at this point. Want to stop? Oh, a little more than an hour. What am I saying? Okay, bye.